We have also the paparazzi. Oh, wow.
Yes, that's for you. So we still wait a few more minutes for the arrival of the all referees. Marco is still missing. Now I think all referees are here, so let's resume our open session. So, okay, in the morning we have the very long session, so the last morning talk is now, we start from the last morning talk, so that it's for the QC for the 3D sensors.
Thank
so
you.
Cynthia, please.
Thank you, Katsuo. So allow me to start from the end for once. And I really would like to start by thanking all the people who made all the measurements that I'm going to show possible. And this is not only including all the people that you see here in the 3D collaboration, but also the people listed here, the test beam crew, with whom we had a very rich and enriching scientific but also personal experience, and in particular Jens, Matthias, Ingrid and the UDET telescope crew, and Nobu Uno, with whom really we spent a very interesting weekend trying to solve cooling problems, and of course Thomas Frisch from IZM, without whom we probably would not have many of the results that we have today. So Daniel already pointed out the requirements for the IBL, so I don't need really to go through that. I try and concentrate what I think we are all looking when talking about a novel technology. So selection criteria, the test we made to really define those criteria, the performance and reproducibility, the stability and reliability. Of course, this is very important for us, the yield qualification, and we also have some pre-production data to sort of support the value that I'm going to show you. Some production and plans in light of these new data that we have, of course, summary and conclusion. Well, we cannot, of course, put on the table experiences with past large systems like the planar sensors have got. 3D is a silicon detector technology which has been specifically designed to be radiation hard. You really have sketches here. I won't enter into that because this is reported in the literature. The only thing I'd like to stress is that the current design parameters have been tuned to optimize the IBL constraints in terms of signal amplitude, noise, bias voltage, and consequent system requirements. And we have been discussing quite extensively on those requirements this morning. So the first prototypes of 3D were available already at the end of the 90s. So a few years later, more industry started producing 3D sensors, adding, of course, different ideas and different designs. Here you have examples of two of such type of designs, and those are the two that, as you all know, you have been choosing for the fast track IBL. So in June 2009, something very important happened, which I'd like to stress because I think is key to try and demonstrate that we really could be present quite early in time rather than going to the much further coming upgrades. 4 facilities decided to join know-how and effort for a common goal: optimize the processor and speed up a parallel, really collaborative industrialization strategy to guarantee a reliable production of 3D sensors. Very challenging, very demanding goal that I will try, in fact, to support today with the presentations I'm going to give you. So reliable production of 3D sensors, so 2, as I just mentioned, were finally selected for the fast track IBL. The remaining 2 still, of course, contribute to the effort and would be happy to intervene if anything, particularly related to risk, would emerge. So you see here the common floor plan wafer layout that was agreed 1 year ago by all the foundries producing 3D. And as you can see here, per wafer, we are producing and we're making 8 FE4 size 3D sensors. So the selection criteria and trace organization are listed here. They are available, of course, in the documents that we provided to the review panel. So I won't really enter into the details, even if, of course, I'm going to recall some of the values that are shown here, just to confirm after the measurement with the PI4 sensors and assemblies that those are really kept and are what is expected. By the way, I should stress that the dimensions and the layout of electrodes for the PI4 IBL sensors is with 2 electrodes per 250 microns. Just as incidentally, I should say that we could also increase the number of electrodes, and this would increase radiation hardness because it goes, of course, with the intra-electrospacing. It would also increase the capacitance, and this is the reason we sort of designed that, to keep signal capacitance and therefore noise at bay. So this is what we are going, in fact, at the end to look at. As I said, at the moment, we have 5 qualification round wafers which are produced at CNM. Qualification means that they really started last year, in fact. And FBK, we have a total, so 5 qualification for a total of 2, for a total of 120 sensors were used to define those criteria. And here is the list of what we used. So there were 32 wafer bond-bonded IZM. They were mounted in Bonn, in Genova, and on boards designed in Bonn. 8 were irradiated in Karlsruhe and Ljubljana. Annealing was performed at CERN using the scenario that we agreed together with our PPS colleagues. Test beam is coming mainly from the CERN SPS with the qualification wafers and devices. Lab tests were performed in parallel in Barcelona, Bonn, CERN, and Genova, just to make sure that there were not really systematic problems related to a particular setup, and electrical test in CNN, FBK, and also Trenton, and simulations that will be also shown later were performed on 3D sensor in Manchester and Trenton, and of course from the group on the IBL. Paris will show that. So this is a table which is summarized.
Sorry, when you say 5 wafers, is that, I mean, how many were started to get 5?
So we started with 20 per foundry, and then Giulio can start. This is the qualification.
But this was were not 20 wafers, they were less, and then they were mixed because they were different thickness.
Okay. So this
I
is.
would say 8 or 9.
No, but then I'll show then later what we are using in terms of wafers, because here it should be also pointed out then when we started the qualification run, some of the wafers they were used to test really some of the parameters that we needed to refine, and so they were just sacrificed.
Are those 230 micron thick?
All are 230 microns. Some, and I'm going to show, and they specified, are 285 microns from CNN, but with the same layout, and so we are using some of them to check yield. But mainly, let's say the results are coming from 230 microns, 200 micron at gauge length.
I also need to understand this number.
Microphone.
Yes, I'm trying.
Sorry. Oops.
So you have you put there 32 were bonded at ICM.
Yeah.
You put 120 sensor on the previous sentence in red. 120 sensor is a lot more than you will get from 5 wafers, right? Because you have 8 per wafer. So I'm a bit confused. 5 is a number that refers to wafers, is a number that refers of batches of wafer.
Let me go on, Gino, and I'll show you. Those are all this is a summary with all the numbers, so you might really get out of this confusion, and I'm sorry if they produced with my numbers that been in some confusion. So for FBK, 16 were unbonded, 5 were not to specs, because when we send those wafers, we did not implement the temporary metal for selection, and therefore really it was a blind type of choice. We were choosing the one in the center of the wafer. Two were irradiated, and those two were both tested in the test beam. And you have here mainly listed all the type of tests that were performed, on which I will go in detail in the next slides. What would be interesting for you to see is this compilation of these FPK assemblies after bonding. So you see here the kind of IVs that we measured after bonding with boards, and a reminder of what we would like to keep and the criteria that we selected on the measurement of wafers. And of course, I show in a moment how this is reproducible, since, of course, as I said before, these were not tested on wafer first.
Sorry, did these results tally or agree with the temporary metal?
I show that.
Okay.
Yes, just to understand, the ones which weren't to specification, were they all for the same reason, or were they different? They're all IV?
These are all the IVs, and for us, those were not in the specification, including this one.
Oh, okay, so the key specification is the IV. That's
For us, not only, you see it here, it is the current, it is an operational voltage, which needs, of course, to be larger than depletion plus 10 volts, and I show you the rationale for choosing this.
No, I'm just asking a simpler question, which was just to understand the ones that you decided not to use.
Yes.
It was based on the IV characteristics.
It was based on these characteristics.
Thank you. Yes, that was all. Thanks.
Yes. The same for CMM. In this case, 16 were mounted. One didn't work, but we do not know the cause. 6 were irradiated, and 3 were tested in the test beam. And again, you will find a summary of their main characteristics. And as before, this is the compilation of all the IVs that we measured after mounting and on board. So, of course, we had some time during the test beam and also in the lab to measure leakage currents and operational voltages. Here I have a compilation of the values that we obtain after irradiation, because of course this is quite important for the system aspects. You have that, well, for both CNM and FPK, the operational voltages, they don't lie on a straight line. Of course, it depends on the temperature. Even if, of course, all operational voltages were maintained at all temperature to which we took the measurements. And here you see leakage currents versus fluence at 4 temperatures, and those were the temperature measured in the climate chamber. So we are not really making any correction of the temperature you see there. It is really the temperature measured in the climate chamber. So what you see here is, I think, a nice confirmation that one of the devices which was on the second row during the irradiation in Karlsruhe indeed got a 10% higher fluence. So 6 times 10 to the 15 neutron equivalent per centimeter seems to be, at least from the currents, really a good estimate of the fluence that this device got. And here you have some numbers which might be significant, which are showing, in fact, the currents per chip at operational voltage. So you can really get an estimate directly of the power dissipation per FE/4. A complete data set of all these measurements is added to the material at the end of the talk. So if you need to have much more detailed values at the point, all the data set is available at the end.
How do you define the operational voltage after irradiation.
So we, yes, we first of all estimate that with simulations, and also we are trying to place ourselves in a region where we can operate stably and getting out the maximum amount of charge that we aspire.
Stably in which sense? I mean, what?
I show you
What
in
is
a
the
moment.
stability parameter?
Stability is, for example, a long time in this condition at fixed temperature where you're not really seeing a variation of the leakage currents. But I show you in a moment what this means. You could also look probably, and this is at the end. Would you like me to go and see? When you're looking at the IV characteristics, a different temperature, you will see that at a certain moment you will go breakdown. So we really need to place ourselves in a position where at the defined temperature we are well below these breakdown points. But LADEX, if you go at the very end, I don't know if this is going to take time. So from that, of course, is an exercise to extract the power dissipation, and we did that again for these 4 values of measured temperature. And you see here what we are obtaining. This is the -15. And you notice here that, of course, you can explain some difference, which, of course, is in contradiction with that for the F2K and the CNN. But we need to understand it might have really temperature variation there. Anyway, these values of the power...
Does that any way correlate definitely with the temperature of the sensor itself? This is the climate chamber temperature.
This is the climate chamber.
So how do I know what the temperature, how do I know what the temperature of the sensor is?
Well, the temperature of the sensor can be estimated by measuring only the leakage current, that particular operational voltage, without any other power on, if you like. So we are using the leakage currents, if you like. But I think it is, of course, a pessimistic value, this one. Because, of course, you will have dissipations. You could have dissipation at that one. So we are trusting that this would be close to the temperature of the sensor, with maybe a higher temperature impact on the sensor itself, because we're not taking into account the dissipation of the sensor.
Let's see.
No, so if you look at the power is quite, if you switch off the chip, the power is low enough that one can assume that the temperature is ambient temperature.
So I
and
will...
this is done after leaving, but otherwise would be worse than that.
Yeah, it's probably higher than that.
Yes,
The temperature is
but
probably
it's
higher.
basically the
Definitely
measurement.
not lower.
Yes, measurement is done going, leaving the board for quite a long time. You read on the board the temperature, okay? You assume that everything is equilibrium, then you apply this power.
By the way, all these measurements were taken with the power of the front end off. So we're really talking, if there is any dissipation here, it's only the dissipation of the sensor. We also have values in time with the power on. And well, I think we're talking about this -5 centigrade with a value like this one. And well, I think we're really well within
The 200.
required.
You have a question?
No, color.
Okay.
Right. So, I'm sorry.
I have a question back. It's back on page 8. I just wanted to ask about the margin between the operating voltage and the breakdown voltage. I mean, you rely on the slope to predict that you're not right on the edge, but your operating voltage specification is 20 and your breakdown voltage is 25.
Yeah, but I'm getting there with the slide I'm showing you now, why we made this choice. Because of course it was a question that Gino asked during the last meeting, and so we were really trying to make sure that we had this one margin to work with. So this is a simulation that really is quite reliable, because we have been testing it already several times now, which shows that a collected charge, TOT if you like in our terms, because I will show those later on, versus bias voltage. We know that with these devices we are reaching a full depletion before any radiation at around just above 5 volts. And so when we are deciding to get to an operational voltage of 20 volts, this really means having 3-4 times this full depletion voltage. So I think it is probably a reasonable margin to play with. Those measurements are showing TOT, so with FEI4 devices versus bias voltage, and these are two devices, and you can see here that showing the bias voltage, the most probable value again reaches a sort of a plateau at around, say, just below 10 volts to look at that. So I think we are confirming this. This was taken with a tuning of ATOT per 20 kilo electrons, which is the same that we use in the test beam data, by the way, and a threshold of 3,200 electrons. Here is the same, so these were FBK sensors. These are so these are CNN sensors. These are FBK sensors. Probably the turn on here is less evident, but again it's showing that we are, in fact, indeed at 20 volt here in the plateau. And there is this blue curve here was taken with a threshold of 1,000 electrons, because I think we need to take advantage of this lower threshold to make sure that we are getting the maximum efficiency. And we saw that at the moment in which we didn't do that, during the test beam, the efficiency went down. I think the message here is that the threshold is not changing with bias voltage. And I show later on more data which are showing somehow this type of behavior. Yes, Bill?
The thickness of these devices is
230 microns.
So is 20,000 the peak of the Landau?
No, the
It's
most
a mean.
probable value is 17,250 expected.
Right.
In fact, we extracted this curve with previous devices, and it combination, in fact, this curve is an average, if you like, of expected charge combining FBK, CNN, and Stanford sensors. And in fact, it is efficiency, so most probable value. Actually, it's a charge in that case. So 17,250, we would expect to get. So noise. Of course, this is one of the key aspects for 3D, because in particular when you have quite a dense amount of closely spaced electrodes, you are expected, and we know, to have a higher 70. Of course, it's only with one sensor there due to the statistics. In the case of the 5 times 10 to the 15th, we measured both for FTK and CNN. And again there, you see that the blue curve are correlating before and after. There is some change in the case of the FTK sensors. We cannot really, we see actually that in the case of the CNN, sorry, with FTK, they have this jump, and the CNN one, in fact, looks as if there is no real change in the noise performance before and after radiation. So these we will have to repeat and understand if there is really something related to that.
I mean, there's again a difference between CNN and FBK. Is there anything in the process that, because you have a whatever 30-40% of increase of noise in the FBK case?
Well, look, this is an FBK. Look at this triangle red and dot. Also, those are 12 before and after radiation. This doesn't show any difference.
So I mean, you have the range 145 to 165, and then you have noise after 5 times 10 to the 15 to 150. So this is not the same.
Well, you have 170 and 250 here, and then you have a non-irradiated and the 2 times 10 to the 15. For example, and yeah, I think we will
So
have.
what's the upper blue line?
The upper blue line, yes, I will use.
That's the
the other
FPK.
blue one is an FPK 5 times 10 to the 15.
Okay, so I'm not mistaken
No, no,
with the number you quote.
No. I said it. I'm quoting the number, so it's perfectly correct. We're going from here with the blue, which is non-irradiated, to the same device after irradiation. And this is the difference between the two. That's it.
That's neutron irradiation.
This is also irradiated with both of them 5 times 10 to the 15. So yes, the irradiation could be
normal working point. It was just recently that we realized that we should have operated at lower threshold. This at least allows us to compare.
Module where you could learn most about sensor behavior was run at 3000 plus.
This is right. This was put in the test beam in the last day where
I
we
understand.
had
I mean,
only 2 hours to run
I'm
with.
just repeating. The
But
module that would have the most weight was run at 3200.
That's it. You're right.
That's it.
But the tuning is what set your results. I'm a bit confused
Well,
by
Gino,
this number 3500.
Sebastian and Andrea can answer this. However, I'd like to stress again that this guy was irradiated.
when we had time to look at it. So we did a quick tuning to put it in the test beam, and then it turned out that the tuning that we did, since it changes from setup to setup, it ended up there. But I think the point is that it's
So, well, this I think was non-irradiated, so somehow it's not really giving a no, it's not true. These are the triangle, and this is number 12, number 12 which is non-irradiated. Sorry about that. Yeah, there are a lot of additional materials. Here, there you go. FBK, currents and power dissipation at different temperatures after irradiation.